Section 9.2, the power method. There are many applications in which some vector x0 in Rn is multiplied repeatedly by an n by n matrix A to produce the sequence x0, ax0, a squared x0, akx0, so on. We call a sequence of this form a power sequence generated by A. If the distinct eigenvalues of a matrix A are lambda 1 through lambda k, and if the absolute value of lambda 1 is larger than the absolute value of lambda 2, and so on through lambda k, then lambda 1 is called the dominant eigenvalue of A. Any eigenvector corresponding to a dominant eigenvalue is called a dominant eigenvector of A. So basically just the biggest in absolute value. Let's find the dominant eigenvalues, if any, of a matrix with distinct eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4 given over here, and of a matrix with these other eigenvalues. So first, let's see, we have the absolute value of lambda 1 is 4. So that means that lambda 1 equals negative 4 is dominant. So that's for our first set. See, even though this one is a bigger number in 3, this one's the bigger absolute value. For our second set, we have that lambda 1, when we take the absolute value, is the same as the absolute value of lambda 2, which is 7, right? These are negative 7 and 7. Since they both have the same absolute value, we have no dominant eigenvalue. One has to be strictly greater than the others in order to have a dominant one. Let A be a symmetric n by n matrix that has a positive dominant eigenvalue lambda. If x0 is a unit vector in Rn that is not orthogonal to the eigenspace corresponding to lambda, then the normalized power sequence x0, x1 given by ax0 divided by its length, x2 given by ax1 divided by its length, and so on through xk and even past that, converges to a unit dominant eigenvector, and the sequence ax1.x1, ax2.x2, ax3.x3, and so on converges to the dominant eigenvalue lambda. So what this does is it provides us with an algorithm for approximating the dominant eigenvalue and a corresponding unit eigenvector of a symmetric matrix A, provided the dominant eigenvalue is positive. This algorithm is called the power method with Euclidean scaling. Basically start with x0, multiply by a, and divide by length to get x1, and then plug in x1 to get x2, and so on. That's our algorithm. So let's do an example. Let's apply the power method with Euclidean scaling to this matrix A with starting vector x0 equal to 1, 0. We'll stop at x5 and compare the resulting approximations to the exact values of the dominant eigenvalue and eigenvector. So first, how about we write out the characteristic polynomial? In this case, that's lambda squared minus 6 lambda plus 5. You could just take lambda minus 3, lambda minus 2, minus 2, minus 2, and then take the determinant and get lambda squared minus 6 lambda minus 5, or do one of the other tricks that we've learned. In any case, this factors as lambda minus 1 times lambda minus 5 equals 0. So that gives us eigenvalues lambda equals 1 and lambda equals 5. Now let's take a look at what happens when we have lambda equals 5. So then we have 2 minus 2 minus 2, 2 by plugging in lambda, setting that equal to 0, 0 allows us to figure out what the eigenvector will be, and reducing this to row echelon form gives us 1 minus 1, 0, and all zeros on the bottom. So that gives us a top equation of x1 minus x2 equals 0. So that tells us that our eigenvector can be given by, or x can be given by tt, which means that the eigenvector that we want can be given by factoring out t and getting 1, 1. So that'll be our eigenvector v1, we'll set that equal to, well, how about we normalize it? So dividing by its length, we get 1 over rad 2, 1 over rad 2, which is approximately 0.7071067811187 and so on. 0.7071067811187. Okay. And I'm writing it out like that so that we can compare it to what we get when we do the power method with scaling, with Euclidean scaling. So I'd start with a times x0. So that's 3, 2, 2, 3 times the vector x0 they gave us was 1, 0. And we get 3, 2 after multiplying. So that means that x1 can be given by a times x0 divided by the length of ax0. So that's 1 over square root of 13 for the length times ax0 is 3, 2 as we computed. So that's approximately 1 over 3.60555 times 3, 2, which ends up being approximately 0.83205.55470. So at first glance, not such a good approximation, but let's keep going and see what x2 should be. So we'll take ax1, and that'll be 3223 times 0.83205.55470, and we'll get 3.60555, 3.32820. So that gives us x2 now by taking ax1, dividing it by its length, and we get for the length that we're dividing by 1 over 4.90682. Multiply that by 3.60555, 3.32820, and we'll end up with about 0.73480, 0.67828. So we're getting a little bit closer to what we should get for the eigenvector. Let's do ax2 now. So we'll take 3, 2, 2, 3, multiply by 0.73480, 0.67828, and we get approximately 3.56097, 3.50445. So that gives us an x3 equal to ax2 over the length of ax2, which is approximately 1 over 4.99616 times 3.5 3.6097, 3.50445. So we get 0.71274, 0.70143. Okay, now we're getting pretty close. But we still have to get x4 and x5. So for ax3, we need, again, 3, 2, 2, 3. This time multiplying by 0.71274, 0.70143, which yields 3.54108, 3.52976. So x4 would be ax3 over the length of ax3, and that's 1 over 4.99985 times 3.54108, 3.52976, giving us 0.70824, 0.70597. And for our last one, ax4, again 3, 2, 2, 3, and multiply by 0.70824, 0.70597. We get 3.53666, 3.53440. So we can now see that x5 is ax4 over ax, the length of ax4. For the length, 1 over 4.99999, and then multiplying that by 3.53666, 3.53440, and we get about 0.70733 and 0.70688. So that took a little while to figure out what that would be, but notice it's pretty close, and if it was a computer doing this, it would take very, very little time to just keep multiplying and dividing like we've been doing. Now let's figure out the approximations for the eigenvalue. So for lambda 1, that's the dot product of ax1 with x1. So we can write that as ax1 transpose times x1, so that we can write the dot product using matrix multiplication. Maybe a computer might like doing that. So we have 3.60555, 3.32820 times 0.83205, 0.55470, giving us 4.84615. So we were supposed to get lambda equals 5. That's pretty close, even after the first one. Let's see if we can get a lot closer, though. So let's look at lambda 2, the second approximation for lambda. So that'll be ax2 x2 dotted with x2, which we rewrite with ax2 transpose x2. So that'll be approximately 3.56097, 3.50445 times 0.73 480, 0.67828, as we previously got, and that'll end up becoming 4.99361. So we are getting closer to 5. Let's do the third approximation now. So ax3 dotted with x3 gives us ax3 transpose times x3, and we'll approximate that with 3.54108, 3.52976 times 0.71274, 0.70143, giving us 4.99974. And our lambda 4. So that's ax4 dotted with x4. We'll write that as ax4 transpose x4. So we'll multiply 3.53666, 3.53440 by 0.70824, 0.70597, giving us 4.99999. Last but not least, for lambda 5, we have ax5 dotted with x5. So ax5 transpose x5. We have 3.53576, 3.53531 times 0.70733, 0.70688, and we have actually rounds to 5, up to 5 decimal places, which is really cool. So we get an excellent approximation for the eigenvalue lambda equals 5 after just doing the power method 5 times. So it's a pretty cool algorithm. You can see how computers would be pretty great at using it. Next, let A be a symmetric n-by-n matrix that has a positive dominant eigenvalue lambda. If x0 or x0 is a non-zero vector in Rn that is not orthogonal to the eigenspace corresponding to lambda, then the sequence x0, x1 given by ax0 divided by max ax0, ax1 divided by max ax1 for x2, axk minus 1 divided by max axk minus 1 for xk, converges to an eigenvector corresponding to lambda, and the sequence ax0 dot x0 over x0 dot x0, and so on, ax1 dot x1 over x1 dot x1 converges to lambda. So what we're saying is that we have another algorithm called the power method with maximum entry scaling, where this max x denotes the maximum absolute value of the entries in a vector x. So max ax0 is the maximum absolute value of the entries in the vector ax0. How about we apply the power method with maximum entry scaling to the matrix and x0 given in the previous example? we'll again stop at x5 and compare the resulting approximations to the exact values and to the approximations we obtained previously. So let's first write out what AX0 is. So that's 3, 2, 2, 3 times 1, 0, which is 3, 2. So therefore, x1 would be x0 divided by the maximum absolute value entry of AX0. So that means it's going to be 1 divided by 3 because the biggest entry is 3. So we'll take 1/3 and multiply that by 3, 2 for AX0. Should be an A over here, right? AX0 is 3, 2. That's our algorithm. Okay, good. So multiplying that, we'll end up with about 1.00000.66667. So that's our x1. So now let's get AX1 and so on. So AX1, we'll get 3, 2, 2, 3 times 1.00000.66667, and that gives us 4.3333, 4.0000. x2 would be given by AX1 divided by max AX1. So that's 1 over 4.3333 times 4.3333 over, oh, not over, this is a matrix, 4.00000, and that gives us about 1.00000.92308. Let's get AX2 now. So 3, 2, 2, 3 times 1.00000.92308, giving us 4.84615, 4.76923. So that x3 is AX2 over the max of AX2. Okay, let's see, max is right over there, so that's 1 over 4.84615 times 4.84615, 4.76923, and we get 1.000.98413. Okay, AX3 time. So that's 3, 2, 2, 3, 1.00000.98413. Okay, multiplying that, we get 4.96825, 4.95238. and therefore x4 is ax3 over max ax3. So that's 1 over 4.6825. Oh, wait, 4.96. I forgot the 9. 96825 times 4.96825, 4.95238, giving us approximately 1.0000.99681. Okay, AX4 now. So 3223 times 1.0000.99681, so that we get 4.99361, 4.99042. X5 would then be AX4 over the max AX4. So that's 1 over 4.99361 times 4.99361, 4.99042, which is about 1.0000.99936. Okay, let's get the lambdas now. So for lambda 1, we have AX1 dotted with X1 over X1 dotted with X1. So that's AX1 transpose times X1 over X1 transpose X1, which gives us about 7.0000 over 1.44444. So that's about 4.84615. I think that's closer than we got the first time, isn't it? Oh no, it's the same, 4.84615. Okay, cool, so let's keep going. Let's do lambda 2 now. So for lambda 2, we have AX2 dotted with, oh, there should be 1 there, dotted with X2 over X2 dot X2, giving us AX2 transpose X2 over X2 transpose X2, which is about 9.24852 over 1.85207, and it's about 4.99361. How about for lambda 3 now? So that'll be AX3 dotted with X3 over X3 dot X3. So that's AX3 transpose X3 over X3 transpose X3, giving us 9.84203 over 1.96851, which is about 4.99974. All right, 2 left, lambda 4, AX4 dotted with X4 over X4 dot X4. So that's AX4 transpose X4 over X4 transpose X4, which is about 9.96808 over 1.99362, and we'll get 4.99999. And for our last one, lambda 5, that's AX5 dotted with X5 over X5 dot X5. So that's AX5 transpose X5 over X5 transpose X5. It ends up being about 9.9360 over 1.99872, which is about 5 on the dot, up to 5 decimal places. Notice that both of these methods produce eigenvectors that correspond to the eigenvalue 5, but these eigenvectors all have a maximum entry of 1, whereas the previous eigenvector approximations we got were just all unit eigenvectors. So they both correspond to lambda equals 5, they're dominant, but in this case we have this guy with a maximum 1 because of our maximum scaling. If lambda is the exact value of the dominant eigenvalue, and if a power method produces the approximation lambda k at the kth iteration, then we call lambda minus lambda k over lambda the relative error in that approximation lambda k. Expressed as a percentage, it is called the percentage error in lambda k, and it is usual to estimate lambda by lambda k and stop computations when the difference between successive iterations divided by lambda k is less than e for a known relative error e. The quantity on the left side is called the estimated relative error in lambda k, and its percentage form is called the estimated percentage error in lambda k. So how about we find the smallest value of k for which the estimated percentage error in lambda k is less than 0.1% for the computations that we did in example 3. So let's look at lambda 2. Well, then we would be taking lambda 2 minus lambda 1 over lambda 2, and we would take the absolute value, and we would get approximately 4.99361 minus 4.84615 over 4.99361. Take the absolute value of that, and we get about 0.02953, which is 2.953%. Okay, so not less than 0.1% yet. Let's go up to lambda 3 then. So lambda 3 minus lambda 2 over lambda 3 in absolute value gives us about 4.99974 minus 4.99361 over 4.99974, and we get about 0.00123, which is 0.123%. All right, so we're getting there. How about for lambda 4? So then we'll take lambda 4 minus lambda 3 over lambda 4. It's about 4.99999 minus 4.99974 over 4.99999, and we get about 0.0005, which is 0.0005%. So it looks like we could stop at lambda 4, but might as well just look at lambda 5 just for the heck of it. How about we see what lambda 5 minus lambda 4 over lambda 5 would be. So that's about 5.00000 minus 4.99999 over 5.00000, and it's about 0.000000. It's about 0%. There's virtually no error once you get to lambda 5. But in any case, k equals 4 was sufficient to answer this problem. So for k equals 4, we have lambda 4 equals 4.99999 has an estimated percentage error less than 0.1%.